Welcome back, class. This is CSE 143. We are covering Building Java Programs, Chapter 14. That's 842, so Chapter 14. If you haven't already figured that out, these slides are by my good friend of over 30 years, Dr. Amelia Gahn. Thank you very much, Amelia. So stacks and queues are an ordered sequence of values. And hopefully you're thinking, how is this different than what we've learned so far? Because you have learned an ordered sequence of values. You've learned them about arrays in, I think, Chapter 7, and then you've recently learned about array lists that are extensible arrays and linked lists, which are more flexible versions of arrays. And those are all ordered sequences of values. And in fact, they're all more flexible than a stack or queue. So you should ask, why are we learning about stacks and queues? And the reason why is because stacks are really the fundamental piece of data that we use in computers. Every single computer that ever has been invented and ever will be invented uses a stack internally. Every time you execute a single statement in Java, like allocating a variable, there's actually probably 3 different stack operations going on in the background. So you can't implement a computer without a stack, and they're super, super critical for anyone who implements a compiler. They're not actually terribly useful in real life, but we learn about them because they are such a flexible and simple data structure. The way that you know about stacks is you know that from recursion, when you were learning recursion last week and you kept on blowing up your computer saying that there was a stack overflow, right, it's using a stack. So stacks are a very simple data structure, but you do need to understand them. Queues are, I've never actually used a queue in production code, although I know that if I had been doing, say, a printer queue or any sort of procedure where you're going to set up the work to be done and some other piece of code is going to do the work in a job-like fashion, then queues are perfect. So all stacks and queues have at least 3 functions, some way to add, some way to remove, and some way to check if it's empty. Don't focus on these names because the names vary between whether we're talking about a stack or a queue. And there are also additional operations that Java gives you, such as size and peek. And later on, we mentioned that you can actually violate the stack and queue by looking in the middle of the stack and queue, which you're not supposed to do. In this class, don't do that. So their example here of stacks is a stack of pancakes, and that's kind of true. Although personally, when I eat pancakes, I always cut right through the center, right? So let me give you a different example of what a stack is that you're probably familiar with. This is the game of solitaire. Most of you have probably at least seen solitaire on the computer, and I should brag that Microsoft Solitaire was just inducted into the Video Game Hall of Fame on May 2nd, 2019. And it was actually done by a friend of mine, Wes Cherry. He and I were summer interns together in the Excel, and then full-time employees in Excel. He wrote the game in 1988, I think it was, and just as a board intern thing. And Wes Cherry, by the way, is one of the greatest programmers of all time. He did a lot of amazing stuff in Excel. Now he runs an apple orchard. But Solitaire is a game you're familiar with because it uses stacks. So I'm terrible at this game. I know that I've got to put the smaller numbers here. This 5 has to go under this 6, and this 4 can go under this 5. And oh, no, it doesn't go there. 10 will go on the jack. No, see, I'm not very good at this game. But the thing is that you really want to access these cards down here below the top of the stack, right? That's always what you want to do, but you can't. They don't let you do that. Ooh, I can put that there, right? That's the only way I can get to the next card is by flipping it over. So that is a stack. That's how you get down to a stack, and it's the same way that our stacks operate in computer science. You can only touch the top item of the stack. And it may be frustrating. It's like, why? Well, it's a good question. Why does Solitaire have this in a stack form? Why can't you touch the cards below? I think most people would agree who play Solitaire that allowing you to touch those cards below would destroy the game, right? And it's similar for computer science, okay? Yeah, you could touch the cards below, the things below in the stack, but it would really ruin the algorithm that you're trying to design to access only the things at the top. So the operations that you have for stacks, you're always just touching the top of the stack. So you can push an item with this method push. You can pop it with this method pop. You can peek to see what the value is without pulling it off. So you're only peeking at the top though. You're just not removing it. You can see how many sizes, how many items are there with size, and you can check to see whether it's empty. So stacks are generic structures. They're parameterized, so you can create a stack of integers or a stack of strings or something like that. And you can actually just call new stack of integer, which is great. I'll explain that that's not always what you can do. We'll talk about with the queues. So stack is one of the oldest classes. They say that it's not well designed because this is not an interface, it's actually an implementable class. But in truth, I think it's actually easier to use this way. And there's a warning here, don't try to access items below the top of the stack. Even though it's possible, you don't want to be doing that. Don't be cheating at solitaire, right? So let's talk about the alternative, queues. So queues, you're all familiar with standing in the line, right? You can only get in at the back of the line, please. And the person who got in first gets out first, right? So in computer science, as I was mentioning, like printer queues is an excellent example that you have seen. The last job that you put in is going to be the last job to actually get printed out. So there is a queue interface, but that is it is an interface. It's an abstract class, so you can't actually create a queue of integers. You actually have to create one of the subclasses. Linked list is one of the subclasses. So you will not be able to just type new queue. You have to type new linked list. So queues, instead of push, they have add. That's going to add them onto the back of the queue. Unfortunately, Amelia really should have reversed the order of these people, because you'll see that in Java they treat the front of the queue as being on the left and the end of the queue is on the right. So remember that. We'll talk about that more. So you can add things instead of push things. You can remove things instead of popping things. So you're going to remove things from the head of the queue. So the first person in is the first person out. You can check whether it's empty, peek at that top element, and take the size as well. So you can transfer items between stacks and queues, and building Java programs in practice, it seems to have this odd fascination with transferring between stacks and queues. But it is a good example, a good practice to make sure you really understand how stacks and queues operate. Here Amelia's written some code. So she takes a stack, and while it's not empty, she pops the top element off the stack and sticks it at the back of the queue. And then that fills up a queue, and then she tries to transfer it back. So while the queue isn't empty, she removes the first item from the queue, the head of the queue, and pushes it onto the top of the stack. And the question is, what happens after you do these two operations? So she's got some code here, and I'm going to drop into Eclipse and show you basically this exact same code with a nice little tool so you can help visualize what's going on. So I got basically the same code here in Eclipse, and I have an add-in installed by a gentleman named Adam Blank. He was a lecturer at the UW. He's now at Caltech, and he wrote a nice little tool called a visualizer. Let's see if I can just get this thing started here. Okay, I've got the visualizer. So we're going to step through this code, and you'll see with this visualizer, it actually gives us a visual representation of what's going on here. So my stack has been created. What the code actually does is allocate this initial group of elements here, and then we're going to create my queue, and you can see my queue actually doesn't really create anything. It's saying that there's 0 elements there, and then we're going to start pushing items onto the stack. So you can see the first item, 0 goes there, 1 goes there, 2 goes there. Now at this point, I just want to illustrate a small problem. Adam has done what probably is the correct thing, which is he's shown them like that plate of pancakes. So the top item he's putting on the top, okay? But internally, if we look at the variables, so if we look at the variables for my stack, this is important here. If we look at the element data, you can see that the elements 0, 1, and 2, in terms of the debugger, they show the exact opposite. They show them from the top down. And really, in terms of memory, if we normally think of memory going from like left to right in a picture, maybe top down. So just to be clear, things are really top down or left to right. And that's the way they're going to be printed out here in a minute as well. All right, let's continue stepping through here. Let's switch back to the visualizer. So we're filling in items 3, 4, 5, and 6. Okay, so sorry, it didn't get to 6. We stopped at 5. So we printed out the items. So I have added, in addition to Mealy's code, I've added in this bottom and top. So it is very important for you to get used to how Java prints this out. Of course, we're using Java's toString. Here, my stack, it's using the toString. So, and also in the debugger, you can see that it prints it out this way. So you need to get used to seeing it left to right. So the bottom of the stack is on the left. The top, where everything is going to be accessed, is on the right. So remember, that's the right is kind of where the action's happening. Okay, so we printed out the stack. It's going to print out the queue, and there's nothing in the queue right now. Now we're going to try transferring. So while this stack isn't empty, we're going to pop the item off the stack. So where's the first item it's going to pop? It's going to be on the right here, or in the debugger, it'll be on the bottom, but unfortunately in Adam's visualizer, it's at the top. So we're going to pop off the 5, and we're going to add it to the queue. So the queue now has one element, the size of 1, and you can see it's a linked list, and that first element is a 5. We're going to go to the second item. So it disappeared from there, and it's now stuck onto here. Next, we're going to take that 3 and bring it over here. And then the 2, and then the 1, and then the 0. So now all of the items are in this linked list here representing the queue. And so we're done with this code, and it's now going to print out the final stack, which is empty. And we've transferred everything to the queue. And this time, Adam's visualizer does it the same way you'll see in Java. So it goes left to right, 5, 4, 3, 2, 1, 0. So the start of the queue is at the 5. The end of the queue is at the 0. So remember, when you go to the grocery store or the mall or the park, and you have to get in the queue, you always have to get in the end of the queue, right? The back of the queue, not the front of the queue. So don't worry too much about the names. In fact, start probably isn't the best name. It's probably the front of the queue, I think would probably be better. But what's important is, again, just like in the stack, it's the right side of this display where all the action's happening. So now we're going to do the opposite operation. We're going to take the queue and we're going to put it on to the stack. Okay, but in this case, the queue, even though we keep on adding stuff onto the right of a queue, when we start removing stuff, now we're going to remove it from the left of the queue. So the first thing that's going to happen, you're going to see this 5 disappear, and it's going to appear here. And then the 4 is going to get stuck here, and then the 3 will show up here, and then the 2, and then the 1, and then the 0. Okay, so we're done transferring it, and now we're going to print out the 2 items. So the stack now has all the items, and the queue has nothing. But let's take a look at the order. So it started out as 0 to 5, with 5 being at the top of that stack of pancakes, right? We ended up with 0 being at the top of that stack of pancakes. So it actually flipped the order by transferring it into a queue and then back into the stack. So that's important when you're doing your practice to remember that. So that flipping may not be what you're expecting, but it's potentially useful. There is a way to get it back to the way that we started. So here, if we start with 1 to 5, we transfer it to the queue, we transfer it to the stack. Now it's 5 to 1. If we do the same operation again, we take that stack, we put it into the queue, we put the queue into the stack, voila, it's back to the same order as before. So again, that's another important thing when you're doing the practices to remember. So stacks to queues, you're going to reverse the order, and if you repeat it again, it'll reverse the order back to the way it was. We've got a cute little piece of code here that goes through and sums the values of the queue by pulling them off and then putting them back. I thought that's an interesting exercise, so why don't we go ahead and take a look at what that actually looks like here. Stepped into the debugger. I've gone to, I have to go one more breakpoint, I think. Actually, let's clear this breakpoint. Go to the next breakpoint. Okay, so here's the code that Amelia just had. And let's bring up the visualizer. So what it's going to do is it's going to check the queue size. So right now the queue size, you can see that actually stores the size for you, is 6. So 0 is less than 6, so we're going to remove. So notice that the size has dropped to 5. There used to be an element here that was the value of 5. That's now stored in sum. Sum is going to add it, and then we're going to add 5 back to the queue. Here's sum right there. There's the value we pulled off. Let's go take a look at, you know what, I'm going to move this down here. I think it'll be easier for you to see. And let's close that for the moment. Okay, so now you can see all the elements. So we're going to add it on to the head of the queue, and the head of the queue is off here. So when we step there, it's still challenging. There, you can see that it added it to the end there. And then it's going to go through, it's going to remove the 4, and now it's going to add that 4 onto the head of the queue over here. I wonder if I can maybe maneuver that out of the way. Maybe we just need to take a look at this. Okay, so we've got the 4 there. And now we're going to get the 3. There goes the 3. Sorry, it's hard to show all of this in the visualizer. So we're removing each item, we're sticking it onto the end. And this code is going to work to successfully sum up all the numbers one at a time. On the other hand, there is one problem with potentially with this code, and that is that it's always checking the queue size. As long as the size is the same after we're done with this body here, we're fine. And in this case, we remove and add. But here's another piece of code where she's trying to do it just by removing the values and then only adding them back in certain cases. And that is going to affect the size. So the size keeps on changing on us. So this code isn't going to work. It's true in general that I oftentimes will, if you have to evaluate something, you don't want to keep on doing that in the conditional. You can store it away, or you can use it and then change your conditional to go through the loop by decrementing or something like that. Here she's fixed the code by taking a size of that queue to start, and then the code will work properly. So this is the end of the lecture slides. There is an additional section in the book, section 14.4, which is an expression evaluator, which I think is a great example, and actually have my students do a RPN, reverse Polish notation expression evaluator, and then that shows you why it is that all computers throughout history have always used stacks. Makes it a very simple example. So I would definitely recommend you take a look at that. Hopefully you've enjoyed this video. If you did, please like and subscribe, and stay tuned for next week.